So my name is Charlie Gracie, and I work on a couple of open source projects, the Eclipse OMR project and Eclipse OpenJ9. And I've been working on JVM technology for about 15 years now. I work at IBM currently as the garbage collection architect. There will be no GC talk in here at all. It's going to be on JITs, as is something I've been learning recently. So a bit of background on the talk is a lot of new runtimes, whether they're written as a new JVM language or smaller other like C runtimes. Usually there's a lot of investment in getting the runtime up and going, which is just having a basic interpreter and focusing on the language. And then things like performance come in, and that's when you start to see JITs or other ways of optimizing the code. So today I'm going to propose sort of a new way of doing things based on some of the technology we provide at the OMR project, on how you could bootstrap a project, a new runtime, and hopefully just write your code once and have both an interpreter and a JIT. So some important disclaimers. I work for IBM, so everything I say here today shouldn't be used for any business decisions without doing your own due diligence on reading into things. So in the talk today, near the end of the talk, we're going to actually go through and do some live coding on trying to get the interpreter up and going with a JIT. But we're going to do this for a runtime that I've written myself, just a small teaching runtime. So I'll give a bit of background on that runtime so it kind of makes more sense as we're getting through the live coding. I'll introduce the OMR project itself and a couple of the components that will be used during the talk. And then we'll jump out into some live coding. And then we'll come back with some future work that we have planned and a quick wrap up. So EL, it's a simple stack-based runtime. And I originally came up with the EL as it's easy language. It's nothing special. Naming's not my strong suit. So it's a language runtime I created for teaching VM basics, in particular to students at a university that I work with and just new hires generally on our JVM team. Getting in and going on our JVM code base at a couple of million lines of code is a bit overwhelming for a lot of new people, so this is a good way to introduce them into some JVM basics. It's a simple stack-based VM like the JVM that everyone here is used to, but it recursively invokes the interpreter when it wants to call methods instead of doing just a swap in the stack space. And it has a very small instruction set, mostly for dealing with handling integer operations. So it's very fast at doing a bunch of math. I can check out the code at my GitHub. So just a quick example. So if you write the program, you write it in some text, but it has a very basic syntax, which then gets compiled out into bytecodes, again, similar to Java VM. So to write one, you start off by giving it a program name, define some functions by function name. It will invoke the main method for any program that you run, and then you can specify some instructions. And it ends with the end declaration. So a quick cover of the instruction set. I'm not going to go into details on all of these. They're kind of a basic set of instructions you might expect for doing some control flow, some math operations, and then the last three are sort of convenience helpers for just being able to show output. Before we go any further, since I'm going to talk about building an interpreter, just wanted to kind of go over quickly basics. Everyone probably saw or wrote something like this in school back when you were doing things or since then. But basically the idea is you loop while there is more bytecodes to handle on your PC, and then you switch over each bytecode based on the PC and handle it appropriately. This is a very simplified case, and you can write your code in C++ to be a lot more efficient than this, but I just wanted a quick example on what an interpreter loop looked like. So the Eclipse OMR project. It was created in March 2016 as a stripped down version of our JVM code. So what we wanted to do, and the key point here is that it's actually dual licensed with an Eclipse public license and Apache license. So it's very open and usable by and consumable by everyone. So the mission was to build a reusable language runtime set of components. So we wanted to be able to accelerate an advancement and innovation in the area of runtime technologies, in particular around garbage collection and just-in-time compilation. And we wanted this set of this toolkit to be able to be used by any new runtime being written, whether by research or somebody writing their own VM. But we wanted to also be able to work with current runtimes. So if you had something like C Ruby or C Python, you could be able to plug in these components without actually forcing those runtimes to change anything about their runtime, because it wouldn't enforce any other semantics on you. So that kind of flows quickly into the goals of OMR. This OMR has no language semantics, so it's up to you. Some of the other solutions that are running, say, on the JVM kind of force you into the Java memory model in certain ways and those types of things, so you do have some restrictions. OMR is for building runtime languages, but it isn't one itself, and any of the components can be used independently without having to use the other components. So a quick sort of cover of the different components. Port and thread, we've broken out into two separate libraries, but this is basically our portability library for being able to bring up a runtime quickly. So you don't have to worry about, is malloc supported on your platform? And yes, there's a lot of platforms where that used to not be true, or how printing works, or virtual memory and those types of things. So this is an abstraction layer. And then there's a garbage collection component, which provides you the ability to use highly scalable GC in any runtime that you wanted to plug it into. And then there's the compiler framework and the JitBuilder framework, which is an easy-to-use API built on top of the compiler technology, which we'll even be talking about a lot today. And of course, there's things like trace for doing high event tracing in your runtime, and a good test framework if you wanted to add improvements or build on this for your own runtime that consumes OMR. So what is the JitBuilder library? This library, it makes it easier for someone to write a JIT. This kind of came from when we first open sourced the project, and I wanted to add a JIT to this Smalltalk VM that I was working on. I looked into our compiler technology, and while it has all this great support, as a newbie in that area of the code base, it was going to be very difficult for me to get something up and going, and I wanted to have something relatively quickly, so I worked with the JIT team to actually go build this library that would help you build JITs or any other sort of runtime acceleration. This library does native code generation, and it's built by having a very descriptive high-level API that's built on top of the OMR compiler. And this allows you to not have to worry about as much of the details to get up and going quickly for a JIT as you would otherwise have to do. That being said, if you want to then dig in deeper, that's completely possible, and you could go take more advantage of the compiler if you wanted to later. So some basics about JitBuilder, because we'll be working with it a bit later. Basically, there's really two APIs, one just for starting up and shutting down. And then once you have a compiler, what you need to do is actually be able to generate a method or a function for your runtime. So for doing that part, we have this class called the MethodBuilder. And anytime you wanted to actually create your own method, to have something generated, you would actually go and create a subclass of this MethodBuilder class and provide some details, and then it would actually be able to go off and generate your method for you. So the sort of two basic parts. One is sort of defining what the API of your method is. So what parameters does it take? What's its return type? What name do you want to be able to so that other methods could call it? Those types of things. And then you have to fill in this build.il method body, which then actually describes what that function or method's going to do. So a very simple method builder example here. This one actually will just go, it defines on the left-hand side, it's sort of the constructor for your subclass. That tells you that the name of the function's increment. It has a single parameter called value, and that has a type of int32, so it's a 32-bit value parameter, and it has a return type of 32 bits as well. So that tells you kind of what your function would look like. So if you were declaring this in C or C++, it would just sort of be a function defined with that return type and that parameter. So the build.il for this method basically is what your method would do. So at this point, this method is actually going to just return the addition of the value you passed in plus 1. So you can see here, you define the parameter with the name of value. On the right-hand side, you can actually see that we're loading that value, and then we're going to add the constant 1 to it and return it. So this is a very simple method, but just to sort of explain the basics of how it works. So how do we compile and execute? I mentioned before there was 2 APIs, the startup and shutdown. You can see those in blue. So if you were writing a program yourself that wanted to be able to generate a method, this is sort of the basic layout of what it would look like. The box in the red is the one that actually calls the compile method builder. And then you can see in the green box where you're actually invoking the function you get back. So anything that JitBuilder generates is actually, it's generating a C callable function. So you can invoke this as if it's any other C function on your system. So what types of things can you do in JitBuilder? Not just a simple add of one. There's all kinds of different services provided. We won't go through all of them here, but it handles different arithmetic operations, conditionals, different types of memory access, control flow, and then there's a few other things for modeling, things like VM states and such. Because in most interpreters you have a stack, maybe arguments, and a bytecode stream, so this provides a way for you to model that so that it can be optimized by the compiler. So when we start coding, one of the things you're going to see a lot, or hear me say the word, is IL value. Basically, this represents an immutable expression tree to our compiler. So you'll see at lots of places, most of the JitBuilder APIs return an IL value and take it as parameters. So in the examples, you can see that I'm getting a constant of the constant of 6. And you could have them at different sizes. I'm just doing these at the 64-bit constant. The add would take 2 different values and return it. And then again, any way that you can use them by pointer, as I am in the top examples, you can actually reference by name as well, just to make it easier to have these symbolic names if people so choose to use them. So what's the expression tree? It's basically built up like this. So if you had this constant, that's going to basically create a load instruction. If then again you had another constant, it's 2 load expressions in their own trees at this point. And then if you added those together, basically at any point you're using this, the result of this, you don't actually have the answer at this point, you just still have a pointer to the tree, which is adding the 2 values together so that it could be executed later. All right, so that's the quick sort of overview on JitBuilder. So Interpreter Builder was something that I've prototyped myself I thought as a need to be able to build interpreters with JITs quickly. So we'll kind of go through it very quickly here. It basically provides an infrastructure for generating an interpreter and a JIT based off of the same code. That was the goal I wanted to get to, because lots of places when you were looking at your some of your code in your interpreter and your JIT, it's very similar. And in a lot of cases, a lot of the simple bytecodes, there's no reason to have the code there twice. So I wanted to be able to build this new infrastructure to allow you to write your code once and be able to have just get a JIT for free after you wrote your interpreter. So this follows along as it's a subclass of MethodBuilder, a very similar set of APIs, one for constructing what your API looks like and then providing the code for it. It introduced a few new services. Since this is actually going to be handling the different bytecodes, we want to register a handler for each one so that we can provide the code for an individual bytecode based on its bytecode index. There's some control flow for jump operations and those types of things. And then some services for accessing data out of your bytecode stream, and an API for accessing any modeling you've done of your virtual machine state if you've chose to model it. So let's go and we'll take a quick look and we'll jump in and build some code here. Nope. So, all right, it is actually somewhat visible. I hope people can see it. We'll go through small bits at a time. So, when I was mentioning before, one of the things you have to do is sort of register a handler for each bytecode you want to do. So for this demo, and all of this code is available at that project at GitHub, in particular, specifically the demo interpreter that will be used here. So basically, for each bytecode that you want your interpreter or JIT to handle, you have to go register this handler, tell it the bytecode index, give it a name so that this is very useful for debugging when you're looking at output-generated code or debugging in a debugger, and then what function that you want to call to be able to handle the code. So I'll scroll down quickly here. For the NOP instruction, basically, that's the world's easiest bytecode, so I won't take the time to implement it here. I have it completely implemented, where it's basically just going to fall through to the next bytecode. Just basically the default fall through, just increments your PC by whatever the value of your bytecode size is, and goes on. I've also started off with an implementation for halt as well, just because it's another simple one, so that we could see if we went to run any program with our demo right now, any test that does anything other than those just returns you an error message built in saying that it doesn't know how to handle the opcode that you've given it. So if we look at a simple test here, we can see we've defined this simple method, which is just going to push some constants, add and return. So if I go back, I'll want to tell my program that I'm now going to handle the push, add, and return bytecodes, and we'll just quickly implement the code for those. To save you guys watching me type incorrectly, I've cached the state at the top as a comment. So this state, as I've modeled my VM with this say that I actually know what the virtual machine state looks like, it has a stack, it has locals, and it has args that can be accessed at any time by referencing through the state. So there's always, for these bytecodes, I've basically put the C code for the C interpreter version that I wrote to test out performance above, just basically so it can show you that it kind of matches up quite well with what you were doing if you were writing the C++ one as well. So the first thing I want to do is actually get the constant out of the bytecode stream. So in this interpreter, anytime you have a push constant, you gave it a value, that's actually just stored in the bytecode stream itself. So I'm going to go through and just fetch that out of the bytecode stream. Everything here has builder objects associated. They basically sort of provide scoping and access to all the underlying services. and I want to actually get out the first immediate. So I'm fetching that. Then I will just do, once I have the value, I want to push it on my stack. And then I want to just say that that's it for this bytecode. Go through and fall through to the next bytecode. Which is so that's all of the code that you would have to write for this. So it's pretty much the same amount of code as on the C++ side. And if you were writing one in C++, you probably have some macros for doing this. So I had some other examples that just aren't as clear what's going on, but you can basically get it so the macros of the two pretty much line up, so the code could even almost be shared. So once we have that, we'll want to do something similar for the add instruction. So this one is going to be fetch the two values off of your stack. Spelling mistake. And what we do here is then we'll want to actually just add the values together. Using the add command. And then you'll push your result onto the stack. And to save some time, and then just fall through to the next bytecode. So that's what the add one looks like. So again, it's very modeled very similarly. We'll skip down to the return bytecode because that's the other one that was required. I won't type this out for everybody, but basically what it's doing is popping the value you want to return. This interpreter has its frames linked together, so you have to unlink the frame from the VM's current frame, and then I just return the value. So if I didn't type any mistakes in there, we should now be able to go and run the first test. And all it was doing was adding a few bytecodes, a few values together. So the next test basically has some printing of some strings and some integers. So I'll demo one of the bytecodes here just to show some other services. So to actually do things like printing, you would actually have to call a helper or define some way to actually print values to the screen. So in this bytecode, I would go and pop off the value I want to print. And then I would call a helper function. So there's a call service where you can go and call functions you've defined. And at the end, I can show the different functions I defined here. It takes one parameter, and it's the value that I want to print. And copy this as well. And I won't go through the string one. I just wanted to show that one because it has the first example of calling a helper. So print string is somewhat similar. It goes and fetches the string you want to print out of a constant pool that was built at compilation and load time. So again, if I've got all my spelling right, and I don't, now we should be able to run the second demo. Oh wait, I haven't registered those bytecodes. So compile one more time. And there we see the message that was printed out. So I'm going to go through and turn on a bunch of code right now so that we can see some more happening. But these bytecodes are all fairly straightforward. Except for jump. So this would be the first example of a different control flow target, so I wanted to show that as well. So for jump, you're actually going to fetch out an immediate for the target instruction of where you want to go to. And then you will just use the jump instruction to go to that target. And there's an extra parameter there, which is whether or not your jumps are relative or absolute. So in this case, in this interpreter, they're all absolute, so they're there. Jump less than, and there's other bytecodes in this interpreter as well, but I'll talk to this one quickly. The jump less than basically does the code at the top. So once you've popped your two values, if left is less than right, then you would just go to that target. Otherwise, you fall through. So the way we've encapsulated this type of jump, it was with a jump if or fall through, so that you actually just pass a condition through to this helper, and it will do the right decision for you for when you're running. So one more compile. And lots of mistakes, sorry. Oh, there's a typo there too. Yep, thank you. And another one. All right, well, this was the last one I was going to type up anyway. Let's just actually discard all my changes for today and go to the working VM. So now we should be able to run the other tests, which we'll look at here in a second. They're basically the exact same test, except for one ends up returning 9 because 6 is greater than 5, and the test directly after that one is doing the opposite jump, so it would return 8. With all of this code now, we also have the ability to actually call other functions from within our function. So if we look at a quick test case for that, test case 5 is going to actually go and call another method. So if I go down here, call test case 5. I see that it called that method and returned the value from it. The interesting part is, now I mentioned that with this code, we have an interpreter. I've shown that the interpreter is working, but when we want to actually be able to generate JIT methods for these two, we have to be able to handle that at the point when we're calling or some other way. In this interpreter, it would happen while we're calling. So I just want to run up quickly. Sorry for the scrolling. See what I have in. Okay. So the call of helper, there was one there. This one is the call with JIT. So this is the one that's currently being used. So it is a bit more complicated. I won't go through all of the bytecodes, the builder code for this, but we will go run a test, test 6, that we'll be able to see, and then we'll look quickly at how this code was implemented. Test 6, which you'll see goes kind of slowly as it's allocating code, running code, and then you'll see in my compile, I print something now to make it obvious on the screen, and then the last of the code, I'll run it again, jumps through very quickly because now this is actually executing JIT code. So the one piece of code we want to look at is this demo method instead of the demo interpreter. It is very similar. It just subclasses a different class, which is the compile MethodBuilder class, but it actually just registers the exact same handlers. So all I had to do was create this class and invoke it at the right place, and it actually goes off and compiles using the exact same code as the interpreter. So then if I look at where that is happening, we saw a print earlier that says attempting to compile and successfully compiled. That is the helper that we end up calling, which will go off and compile using this compile method builder for the demo method based on the actual function that we're trying to invoke right now. So it'll go and generate code for the specific bytecodes of this method and then invoke it. And then we have a JIT method from then on. So in the call bytecode, the major difference is you'll see at some point we would do a compile. I don't want to go into all the details about how I decided that. In this case, it's simple after a count of 10 executions. But all we would do at that point is either call the, down here, either call the JIT method or we just call the interpreter again. And that is basically the only code I had to change in the general interpreter, but that would also is used for the JIT as well. So at this point, we have all of that code and we can run a bunch of tests. So I have one example here or a few. So running an iterative Fibonacci example, which is basically just a giant loop doing some math. So you see some interpreter times of about 120 milliseconds. That is very close to the speed I can get at the highly optimized C interpreter version. But then after we've executed a few times, we're down in the 5 to 6 millisecond range. So if you had a small runtime and you use this technology, seeing something like some math operations become 20x faster is not out of the question, and a very easy amount of time, a very quick amount of time. And if I look here, I'll just run one other example. Oh, sorry, I don't have enough of the bytecodes for that one. But because it's just the demo, it doesn't support everything at this point for what we've done today. But you can see that we have a lot of performance that we can get at that point, and it can make some really significant improvements. So we'll jump back to the slides. All right. So right now, this JitBuilder interpreter builder code is quite good. I haven't taken advantage of a lot of the features of JitBuilder in my examples or things yet. So what I want to do as some follow-on work is show people how they can write a few other lines of code, and then you could have method inlining from one call to the other. So then you could see things like even some recursive Fibonacci become significantly faster because it can even inline multiple levels of the calls themselves in through functions like that. I want to provide a asynchronous compile thread that you could link into your runtime to use, because right now all of these compilations are synchronous by default. So I wanted to provide something very simple for people to be able to go off and add that to their runtime. I want to, since we have control of the interpreter in this point and it's easy to plug in data, I would like to be able to generate to be able to strobe off some interpreter profiling to be able to do better generated code on the JIT side. Another one would be to provide, this is not just for stack-based VMs, so I'll do a register-based example as well. And sort of the big feature that I want to see us finish in the next year is actually providing more than C++ bindings for this API. So right now, all of the services that I was calling on JitBuilder APIs and on the interpreter builder, they're all being generated from a client API generator. The next step we want to do is add language bindings for Java, Ruby, Python, some other languages like that. And then you'll be able to actually use this API while you're writing code in whatever your runtime is, as long as the bindings are supported. So this could actually start to make some of the other JVM languages have a bit more control or flexibility in how JITting's actually happening for them on their JVM, because you'll actually be able to have more control because you're actually calling the APIs themselves and having things generated. So to wrap up, the Eclipse OMR project has been out there for a couple of years now. It is and was and still is the basis for the OpenJ9 Java VM. So this code is industry tested. It's a very well written, or mostly well written. Oh no. Hello? Seem to be working very well. Very slow.
Can you give me 2?
Am I back? Perfect. Thank you. So with the OMR project being out there, it's a very open project. We actually are starting to get some outside contributors, and everyone's welcome to show up, ask questions, contribute code if you would like. All of the demo stuff I did today is available either at the OMR project for me, under the Conf 2019 branch, and same as the EL project. And that's it. So the first question is, which software and hardware platforms are supported by OMR? So currently, Linux on x86, PowerPC, and 390 are supported. Windows is supported. OS X, Mac OS X is supported. ZOS mainframes, if all of you guys have those in your basement for hacking on. What else am I forgetting? Linux, ARM, and Arch64 support is almost complete. And very recently, a contributor has opened up a pull request for RISC-V on Linux. Oh, and AIX as well. So what's your opinion on various other tools for creating languages? For example, Antler or Bison. For actually the language portion and for the compiler of my project I have there, it actually is using Antler itself to actually go and do all of the parsing and code generation. As far as doing the runtime itself, those are more for the parser side and not actually the runtime. So it's not exactly comparable in my opinion. The next question is, what about speculations? Can I transfer to the interpreter in the middle of JIT code? Is there any support for that, or does one have to code it manually? In the OMR compiler itself, there is support for transitioning back and forth between the interpreter, from JIT to interpreter. At the JitBuilder level, at this point, we have not exposed that. It's one of the things we're working on. But it should be something that is possible for us to complete. And the last question, are there C bindings for JitBuilder? Right now, there is somebody working on C bindings. They're not completed as of yet, but there is a person with open pull requests working on that pretty regularly. Okay, that's the last of the questions in the website. Does anyone else have any other questions? Okay, thank you for your time. It's really appreciated. I'm glad everyone took their time to come in and listen to my talk. Thank you.